Before I go to section 10C on page 10 of your notes, I want to look at the very bottom of page 9 and recap how the number E comes about, because that directly leads into what we're going to do on page 10. So recall that we talked about different ways to calculate investments. The first equation we looked at calculated investments when interest was added or compounded once per year. So we call it compounded yearly. Then we looked at a formula that talked about how we could calculate interest if it was compounded multiple times per year. And so we saw it compounded quarterly, monthly, and daily, where we would change n to 4, and then to 12, and then to 365. And we noticed that when we compounded the interest more than once a year, we got a little bit more interest than when we compounded once a year. But as we compounded more often, that increase in interest kept getting smaller and smaller. So then I had you look at the difference between these two equations. Here we have 1 plus r, and here we have 1 plus r over n to the nth. So if we take the r out and we just look at what happens to 1 plus 1 over n to the nth power as n gets bigger and bigger. So let's make n 10, then 100, then 1,000, then 10,000, 100,000, a million, 10 to the 8th, which would be 100 million, and a billion. No, actually 10 billion, I think. What happens to the quantity 1 plus 1 over n to the n power? And it turns out that the number gets bigger and bigger, but as we increase n, it gets bigger by a smaller amount. And pretty soon we're just adding decimal place differences way down the line, and it starts to settle down to the same beginning decimal places. And it turns out that this number is the number E, which can be found on your calculator, not on your keyboard E, but using the pi button and using this bold letter E, and then we do Control Enter, and we get this number. And you can see it has more decimal places. It's actually the same number. It's the same as pi in that it is a non-repeating, non-terminating decimal. It goes on forever, never a repeating, a regularly repeating sequence. This number is the most important number in calculus, just like pi is the most important number in geometry. Now, how does that relate to what we're doing in this unit? Well, this, and before I say that, this is said in mathematics. We can say when one number approaches another number as a certain number goes to infinity. So we can say here, and I wrote this wrong, this should say as n goes to infinity, as n goes to infinity, not x goes to infinity. We say as n gets bigger and bigger, the number approaches e. In mathematical symbolic language, we say the limit as n goes to infinity of 1 plus 1 over n to the nth power is e. In other words, it reaches a limit where it doesn't get any bigger, and that limit that it reaches is the number e. So we can take our base of our exponent, which in this case is 1 plus r, and in this case is 1 plus r over n to the nth power, because we can think of raising that to the t power, and change it just to e to the r, the number e raised to the interest rate r, or the rate of change r. So this would be the base we would use if interest is added one time a year. This is if interest is added n times a year, and this is if interest is added an infinite number of times a year, which we call continuous compounding. And that leads us to the formula. Instead of p times 1 plus r to the t, or this other formula, we get p times e to the r to the t power, or p e to the rt. So that's what we're going to be, this is the equation we're going to be using to calculate interest. Oh, and by the way, if we use that to calculate the interest on our previous problem, and we substituted 2,000 for p and 0.04 for the interest rate and 5 for the number of years, let's just go ahead and do that, we would get 2,000 times e to the 0.04 times 5 power, and we find out we get $2,442.81, which is just 3 cents more than we got when we compounded 365 days of the year, 365 times per year. Okay, so let's move on then to page 10. That is not the page I want to move on to. It's actually down here. And let's use this equation to solve some problems. At 4% interest per year compounded continuously, how many years would it take an initial investment of $2,000, okay, so that's P, of course, and this is our interest rate, to double to $4,000, so this would be A. So we're going to say $4,000 is equal to my starting amount, $2,000, times e to the 0.04t, and I want to solve this for t. So the base of the exponent is e. 2,000 is not affected by this exponent, so the first thing I have to do is divide both sides by 2,000. And when I do that, I just end up with 2 on the left-hand side of the equation. So 2 equals e to the 0.04t. Now, if I had been doing this using other methods, I would just take the log of both sides or write it in log form. So e to the 0.04t, remember e is just a number here, so I could take the log of both sides or write it in log form. Now I'm going to recommend in this case that you write it in log form. You can certainly take log of both sides and you can solve it and get the right answer, but I want you to get comfortable with something called the natural log. So I want to define natural log. Natural log is equal to log base e, which is abbreviated ln. And the reason it's abbreviated ln instead of nl is because the mathematician that came up with this idea was French, and they put their adjectives after their nouns. So it would be log naturel, ln. So when I want to write log base e of something, I can also write ln. Just like if I want to write log base 10, it's just log. Log base e is just ln. That's the way we abbreviate it. So if I were putting this in log form, I could write log base e of 2 equals the exponent 0.04t. But I could also write this as natural log of 2 equals 0.04t. Natural log is one of the 2 logs used on every scientific calculator. There'll be a log button, log, log base 10, and there'll be an ln button, natural log. On our calculator, you're going to find this above the button that says e to the x. So it's above the e to the x button on your calculator. Now, the only thing I have to do to finish solving this is divide by 0.04 and get t. So let's do this on the calculator. So there's my e to the x button over here. So natural log of 2 divided by 0.04. So this tells me it would take about 17.3 years for me to double my money from $2,000 to $4,000. Say 17.4 or 17.3? 17.3. Notice it really wouldn't matter how much money I started and ended with, as long as the starting amount and the ending amount is twice the starting amount. So I could have started with $20 and gone to $40, or $2 million and gone to $4 million. Either way, this would have ended up being 2 equals e to the 0.04t, and I would have ended up with 17.3 years to double the money at 4% interest. So let's take another look. Let's take a look at the next problem. What interest rate would be needed for the initial investment to double in only 6 years? Okay, so now what I am given is a t. So this is my t, and I want to know what r is. So I'm going to say 4,000 is equal to 2,000 e to the r times 6, or 6r. Once again, if I divide both sides by 2,000, I get 2 equals e to, then I'll just put 6r. Now, writing this in log form, it would be log base e of 2, or natural log of 2 is equal to 6r. And then I would just divide both sides by 6. So natural log of 2 divided by 6 equals r. And this was going to tell me the interest rate I would need in order for my money to double in 6 years instead of in 17 years. So I'm going to need a higher interest rate. So going to the calculator here, I'm going to do natural log of 2 divided by 6. Control Enter. 0.1155. So that's about 11.5% interest, or 11.6% interest if we round. 0.1155 or 11.55% interest. Now I want to show you something interesting called the rule of 72, and this is not something that you have to necessarily know for this class, but it's something you may have heard of, and I just want to introduce this idea to you. So I'm just going to open up a new page just to have a place to write. So let's say I wanted to solve the same equation to find how long it would take me to double my interest, or double my amount of money at a 6% interest rate. So instead of dividing by 4%, which ended up with 17.3 years, I divide by 6%. I'm solving the same equation, but just instead of 0.04, it's 0.06. So I end up with natural log of 2 divided by 0.06. That gives me 11.5 years. If I wanted to see how long it would take me to double my money at 8% interest, it would only take about 8.7 years. And at 10%, it would only take about 6.9 years to double my money. So I wrote all of these down here, the number of years to double your money at various interest rates. And then I want to introduce to you something called the rule of 72. And someone found out that 72 divided by the interest rate gives you the approximate number of years that it takes you to double your money. So if we do 72 divided by 4, we end up getting 18, pretty close to 17.3. 72 divided by 6 is 12, pretty close to 11.5. 72 divided by 8 is 9, pretty close to 8.7. 72 divided by 10 is equal to 7.2, pretty close to 6.9, or 6.9. It turns out that natural log of 2 is equal to 0.69 something. So if I'd done the rule of 69, I would have actually gotten numbers closer to these values. But 72 was picked because 72 is divisible by so many numbers. So it's really easy to divide 72 by a lot of numbers and get really quick answers. And these are pretty good rules of thumb for how long it takes you to double your money at various interest rates. So just thought I'd show you that kind of an interesting, fun fact. Okay, for the last part of this section is how do you change between a, quote, regular number and base E? So, for example, we had we have the equation a times 1 plus or minus r to the t power, and now we could have a times e to the some coefficient times t, like we had a times e to the 0.04 t when we did the interest rate. So think about our example in number 2, and this should actually say f of t and not f of x. F of t, since we're using t as our input variable, f of t is 2 million times 0.95 to the t power. We used that when we had a 2 million population and it was decreasing at a rate of 5% per year. And so we did 1 minus 0.05 and got 0.95 here. So what I want you to notice is that this particular equation could be written f of t is equal to a times the quantity e to the k to the t power, because that would give me e to the kt power. So that means the difference between this equation and this equation is the base of the exponent. So here we have 1 plus or minus r, here we have e to the k. So if I want to change this equation into something involving e, the base 0.95 is going to have to be changed to e to the k. So if I set 0.95 equal to e to the k and solve for k, I would have the formula in the form with base e. So once again, I'm going to say log base e of 0.95 equals k, which means, I'm going to go ahead and write this down. Log base e of 0.95 equals k, but remember we're going to write this as natural log of 0.95 equals k. So in order to change the base 0.95 to an e raised to a power, the power is just going to be natural log of 0.95. And natural log of 0.95, if I do that on my calculator, happens to be this number, negative 0.05129. So I could write this equation as f of t is equal to 2 million e to the negative 0.05129 t. And other than some rounding, because this is a rounded number, I would get the same answers as I would get with this formula. It's going to be a little off because this is rounded. Now you might think, why would I even want to bother with base e when 0.95 is so understandable and easy to use? In this situation, yes, I would probably stick with 0.95. But I want you to be able to go back and forth, because in calculus, using base e actually makes your life easier. So I want you to be really comfortable with base e and how these two are related to one another.